Hi everyone, welcome to the second experiment of Digital Design Laboratory. This experiment has two parts. So the first part is about designing and implementing a BCD to 7 segment decoder, and the second part is to simulate a 4-bit adder. Let us start with the first part, which is on BCD to 7 segment. So you all know that BCD stands for binary coded decimal, where essentially we are trying to represent only those binary values who have a decimal equivalent between 0 and 9. BCD refers to binary numbers corresponding to 0 to 9 digits, and you already know what is a 7-segment decoder. 7-segment essentially has 7 LEDs, and when a certain number of certain combination of LEDs are on, you see a certain number displayed on the 7-segment. Such a decoder would have a 4-bit input, and like we discussed in class, we will try and represent numbers, because these are all positional number systems. We will represent it from MSB to LSB. So this is the most significant bit and A0 is the least significant bit. So A3, A2, A1, A0 is our input binary number, BCD number, and of course the output would have corresponding 7 segments. It's actually 8. The 8th segment is corresponding to the decimal point. It is not relevant to us in this experiment. So we will stick to just these A all the way through G. Since a 7 segment can show maximum number 9, that means binary combinations from 10 onwards, that means 1010 onwards, they come under the category of don't care conditions. So when we take that into account and we try and minimize each of these Boolean expressions for A, B, C, D, E and F, each of these 7 LEDs, we come up with, after minimization through K-maps, we come up with these expressions. Okay. So to understand how this truth table is made and then minimized using K-maps, please revisit the previous video on combinational logic circuits. Knowing that these expressions are already there, let us first start with writing the Verilog module for such a converter. So the module of 7-segment display can look something like this. It takes 4 inputs and it gives 7 outputs. So the logical expressions for A, B, C, D and other LEDs, they have been written here in the form of the assigned statements. This code is true under the assumption that an LED will glow if the connection given to it is high, right? This is true for a common cathode kind of 7-segment display. 7-segment displays are of 2 types, common cathode and common anodes, right? Now know that in common cathode SSD, the N side of each of these LEDs is connected to a common terminal. You can see this, right? All these, they are all actually connected to the ground. So cathodes are connected to this ground terminal. So if you outside this 7-segment, if you actually connect this to ground, all you need to do for a particular segment to glow, you need to give a high input over there. So for example, I want this segment to glow. That means to the B terminal, I should give a binary value 1, right? So what we have discussed earlier in terms of the truth table, the function, that is all applicable to this common cathode kind of SSD. That means in a common cathode 7-segment display, if you want a particular LED to glow, you need to give it a high input. Okay. It is the exact opposite in the common anode SSD. You notice that in the common anode SSD, it is the P side of each of these segments which are all connected. They are all connected to each other, so they have a common terminal, and here this should be connected to plus VCC, like 3.3 or 5 volt, something like that. Since the P sides are already connected to VCC, for any of these LEDs to be forward biased, we need that the N side, which is actually going to the ABCDE terminals, this should be connected to ground, or this should have a low input, or basically saying logic value 0. If this is connected to logic value 0 and the N side, P side is connected to VCC, only then will a particular LED glow, right? So if I need this LED to glow in a common anode SSD, I will need to give it 0 output. Okay, so it is not that we have to recalculate the whole thing all over again. Instead of having a high input for a particular LED to glow, we're going to give a low input. So whatever function you had, just that there is a not that I have added in front of all of these expressions. Okay, so it is important that in lab you are first aware of whether you have a common anode 7-segment display or a common cathode 7-segment display, because the code will depend on that. So be careful about which type of SSD you're using. Now in the lab you may be given common cathode so that you really don't have to change anything from this expression. But in this video I am using a common anode SSD. So I'll be using this expression. So now how do we connect this, right? Our expression is fine, and we could also write a test bench with different values, or we could use a force clock or something to check whether this works fine. But how do we connect the inputs and outputs through the pink board? So if we look at the pink board, we already know that the pink board has two slide switches which can be used for inputs. It has 4 of these push buttons which can also be used for inputs, and it has these 4 LEDs, right? So in the scope of this experiment, what we are hoping is that we will give inputs on these 4 buttons. Okay? So A3, A2, A1 and A0. We are hoping that it is in this order from most significant bit to least significant bit that we will give inputs. So for example, I am pressing just this button, right? So this combination will correspond to 0, 1, 0, 0. Only this button is pressed, nothing else. So this means this is binary 8 or BCD8. It should show me number 8 on the 7-segment display. So how do I now connect the 7-segment display here? This is where we take help of a very useful feature of the pink board, which is called PMOD. PMOD stands for peripheral module. So on the pink board, we have two PMODs, which are these blocks. Okay? So this is called PMOD A and this is PMOD B. Peripheral modules can be used for connecting peripherals. That means anything additional that you want to add, like more LEDs or more switches or 7-segment display or any other device for that matter, right? So since this is A and this is B, in this experiment we will be looking at PMOD B. Know that whatever we are deciding here about inputs being given to these buttons and output being given to PMOD, these things have to be updated in the XDC file, right? So let's take a better look at how PMOD terminals are actually defined. So this is how PMOD terminals look like. So this is pin number 1, 2, 3, 4, 5 and 6. This is 7, 8, 9, 10, 11 and 12. This diagram is available in the user manual of pink board, and you can see that these two pins, pin number 6 and 12 are connected to VCC and 5 and 11 are connected to ground already, right? So when the pink board is powered, this is automatically connected to ground and this is automatically connected to, I think, 3.3 volts. Okay. So now depending on whether you are using common cathode SSD or common anode SSD, you will have to make a decision on whether you want to connect this common terminal. There's a common terminal, whether that needs to go to ground or whether that needs to go to VCC. So in this particular case, I am using common anode. Okay. In the lab, you will be using common cathode. So because I'm using common anode, I'm going to connect this terminal of my 7-segment display to one of these two pins. So let us say I'm connecting it to pin number 6. But in the lab, when you are making this connection, if you're using common cathode, make sure that you connect this terminal to pin number 5 or 11, whichever. Right? Now, from the user manual of Zinc, I need, because I need to make these changes in the XTC file, right? So it's important that we know what is the name of the Zinc pin and which pin number does it correspond to. I am using common anode, so I will simply take that common terminal and connect it to pin number 6 for the rest of the things. So on pin number 1, I'm giving A, B, C, D, 5 and 6 not giving anything, F and G, right? So it is these pins 1, 2, 3, 4 and 7, 8, 9 to which I will be connecting my 7 segment display, right? So I decided that I'm going to connect A over here, I will connect B over here, then C to this pin, D to this pin, E will go to this pin, F to this, and G to this. Okay, so this is on the pink board and this is mounted on my breadboard. So these are the connections I need to make, and because this is common anode, goes without saying that this VCC will also go to say pin number 6. These are the connections that I need to make through with the jumper wire between the pink board and the 7 segment display. ABCDs, the lowercase ABCDs are the output ports of my Verilog module, and we decided that this is how they are linked with the pin numbers. So in the XTC file, I need to change the input ports for these particular pins. Okay. So let us see how this looks like in Vivado. So this is how the Vivado project looks like. Under design sources, we have one module whose code looks like this. Note that I'm using the complemented form. I've put a not operator in front of each of these expressions. This is my main module. It takes these 4 as the input and generates these 7 as the output. Next, coming to the XTC file, and if we open this XTC file, remember that we need to make only 2 types of changes. One is to set the buttons where we decided to give inputs. So if I go back to the manual and I now look at the definitions of buttons, because it is the buttons on which we decided we will be giving inputs. So we decided that this is the leftmost button on the board. So we decided that we'll give A3 on this, A2 on this, A1 on this, and A0 on this. That means L19 has to be mapped to A3, L20 to A2, D20 to A1, and D19 to A0. So if we just look back, so L19, L20, D20, D19, so we have just changed the name of the ports for these 4 buttons. So our inputs are set. Now we need to set the PMOD options as well. On the PMOD, we decided that W14 will get port A, Y14 will get port B, this will get C, D, and then E, F, and G, right? You don't have to set any ports on these pins as such in the XTC file. They are already connected, right? So they are ground and power. They are not really input output pins. Only these 8 are the input output pins. Okay, so this correlation is also to be updated in this XTC file. So you notice that this is what is done. Okay, and we don't use the last one. This is all you need to do in the XTC file. You save this XTC file. Our 7 segment display is also ready. If you wish, you can simulate this and use a forced clock version or any other test bench to simulate the results. I'm going to jump right away to generate bitstream. So this is how the PMOD B terminal looks like on the pink board. made the connections as discussed. Let us check this circuit. So I have now generated the bit stream and opened Program Manager, loaded that bit stream onto this board. Now I'm going to give input to these push buttons and see what happens. So right now the 7 segment shows 0. If I press the first button, this means 0, 0, 0, 1, and you can see that it shows a display of 1. If I press the second digit, that means 0, 0, 1, 0, it showed the number 2. If I now press the last two bits, last two buttons simultaneously, I am giving an input of 0, 0, 1, 1. It shows me number 3, and so on. And pressing all three buttons, 1117, 10008, 1001 as 9. Okay. The next part of this experiment is on implementing a 4-bit adder. So we have already discussed in class how a 4-bit adder can be generated using using 4 full adders. So a 4-bit adder should add two 4-bit numbers. So suppose the two numbers are A and B. So this is a 4-bit number A3, A2, A1, A0, and B is B3, B2, B1, B0. How you would use 4 full adder modules is that in the first full adder you will give the least significant bits of the two numbers, say A0 and B0. There is always a carry in, and in this case that carry in can be 0. The output of the full adder will be a sum bit and a carry bit. That carry propagates to the next full adder, or rather ripples through this entire full adder, right? So the sum of such a 4-bit adder is a 4-bit number, S3, S2, S1, S0, and the carry is simply C3, that is the carry of the last stage. If you're looking at this from a Verilog point of view, know that you will have to write a full adder module just like how you write the half adder module. So if you're looking at it from a hierarchical point of view, this 4-bit adder is the top level module, and the full adder or rather 4 such instances of full adder, these correspond to the lower order modules. Now for the purpose of simulation, we will also have a test bench where we are going to call this 4-bit adder, right? So if we are looking overall, including the test bench, it is the test bench which is the highest order module, because the test bench creates an instance of this 4-bit adder which in turn contains 4 instances of the full adder module. The hierarchical structure of such Verilog codes should be clear to you. Now let us look at how this code is going to look like. So as we expected, the full adder module looks something like this. We are calling it full underscore adder, and we are defining 3 inputs in this particular order, X, Y, and Cin. The outputs are saved in 2 ports, sum and cout. Know that as opposed to the logical expressions that we have been using in earlier examples, you can actually represent binary addition directly with the help of Verilog operator of addition. Okay. So in this case, we could also have written it as x plus y plus cin, or so we know that we could have written that cout is nothing but x and y, or x and cin, or y and cin. We could have written it like this also, and sum is just XOR of these 3 inputs. So both ways are fine. So this is the full adder module, and now to create a 4-bit adder using this module, we write the next module. And now look at how inputs are defined. So know that I have written the whole thing, input A, everything here itself. I could have just written A, B, C and S over here and then later defined input and output. Okay, so I'm just trying to make the code a little more compact, which is why the size of this register and whether it's input output is defined right away in this statement itself. Okay. So what does this mean? This module will also take two inputs A and B and generate output S and CO, CO standing for carry out. But know that now these A, B are not 1-bit numbers anymore. They are actually 4-bit registers. So when we say 3, 0, we basically mean that A is a register of 4 bits. 3 is the most significant position, 2, 1, 0. Okay. So you have A3, A2, A1 and A0. This is what this term means. Okay. So similarly, B is also a 4-bit number, S is also a 4-bit number, C out is just a. Now that we have defined inputs and outputs,
1-bit
these
number.
intermediate carries also play a role, right? But they are neither input ports nor output ports if you look at the big picture of this big 4-bit adder. So this array which stores carry bits at every stage, let that be defined through the keyword wire. Okay, so this stores carries. So now we create 4 instances of the full adder module defined above. The first instance corresponding to the least significant bit, let us call it something like FA0. It takes a 1-bit input, which is the least significant bit of A, the least significant bit of B, and takes carry in 0, and it generates sum and carry, all of which are 1 bit long. Okay. Know that this full adder adds 3 1-bit numbers, right? So the output of full add, so all these are 1 bit long. The next instantiation is for the second bit, where you take the second bit of the two numbers A and B and you take the carry which was generated from the previous case and take that as the third input and generate sum and carry. In the third instance, again take this carry generated in the previous case as the input, and like this you can write the 4 instances and end the module. Okay. So this is how your 4-bit adder module looks like. But to test whether this is correct or not, does this work the way it is supposed to be, we also need to create a test bench, right? So in this test bench, we will be giving different combinations of A and B, 4-bit inputs of A and B, and displaying the sum and carry. This is how the test bench code looks like. I'm calling this module as test bench underscore 4-bit adder. A and B, because these values are going to change in the procedural statements of initial, begin to end, because these are procedural statements, and since the values of A and B are within this procedural statement and they are the ones that are changing, these have to be defined with the keyword reg, and others which are intermediate can be defined by the keyword wire. Okay. So now creating an instance of the 4-bit adder defined in the previous page, and the name of that submodule is this. Note that I'm showing this in 2 different pages. You could easily include all this within the same code. Just need to keep in mind that then in that case, the name of that file should not be any of these modules. Write some other name. If you create a file, a .v file under design sources with some other name, then all these 3 modules can be put within the same code. Okay. So creating an instance of the 4-bit adder, giving it a name and defining what the inputs are and the outputs are. Okay. We start with the procedural statement initial begin and say give at least 6 cases. This is what we are trying to do. This is the kind of operation we are trying to reflect. So choose those values of A and B, choose some of them which give us a 0 carry out, and some of them which give us a 1 carry out. Don't just take only one type of numbers. Okay, so for example, in the first case, 3 plus 5, that means A is defined as 0011. This statement basically means a 4-bit binary number 0011. So when I say 4 dash B, this means a 4-bit binary number, and what is that number I want? 0011, which means decimal 3, binary 0011, right? So this is what I want A to be. So this means A is nothing but 0011, and we say B is equal to 4-bit binary number 0101. So B is 0101. Okay. So once you add these two, what should you get? 1 plus 1 is 10, 10, 10, and 1, right? So the last carry, the C out, is actually 0. For this particular test case, you should get output as 1000. And set this value for A and B, and then wait for 20 nanoseconds. The hash 20 means 20 time units. By default, on the top of this code, if you see something like time scale, say 1 nanosecond slash 1 picosecond, if this is what is written, what this basically means is that the default time unit is 1 nanoseconds, and the precision of time means the minute incremental values at which you can still observe change in input, that is 1 picosecond. So if this is what is defined on the top of your code, the default time unit is nanoseconds. So when you say hash 20, it means wait for 20 nanoseconds. Okay. And like this, take several cases. In some cases you should get carry as 1, in some cases you should get carry out as 0. Then you finish and end this module. Know that for test bench, since we have defined S, which is a 4-bit number, and C out with wire, these two will be actually shown in our timing diagram. So both A and B, the 4-bit values, and this S and C out, this will be shown in our timing diagram. Alright, so let us see how this looks like. So I have opened the Vivado project. Let me show you the module under design source. So on top you see time scale is defined like this. It is more commonly it's written already by default. This is how my full adder module looks like. This is how my 4-bit adder module looks like. And this is how my test bench looks like. Know that I have given the name of the file as 4-bit adder, which is not any of these module names. Now when I will run simulation, expand it and zoom fit, you can see that it is showing me the corresponding A and B values, 4-bit values, and the corresponding sum and C out. So the first case 0011 and 0101, as we discussed, the output will be 1000, that is the sum, and carry is 0, right? So carry is 0. The second case, the two values are 1100 and 1010. If you add them up, you get the sum comes out to be 0110, and there is a carry out of 1. So this, the last row is actually showing you the carry out. You see carry out is 1 and this is sum. Okay. So like this, please show for at least say 6 different values of inputs in your test bench. Insert the screenshot of this diagram in your report. For this experiment, you only need to do up to simulation, and there is no implementation needed. I hope you have fun. Thank you.